Okay, so exponential growth and decay is section 7.4. Okay, 7.4. All right. And let me just take you through a little bit of a tour here. So, and let's see, you're seeing what I'm seeing. Good, okay. So one of the models for population growth is the assumption that the population grows at a rate proportional to the size of the population. Okay, in other words, the rate of growth, dp dt, of the population is equal to kp. So the growth rate of the population is proportional to the population at that time. Okay, is it a reasonable assumption? Well, for bacteria, it is reasonable. Now, I want to be a little bit, but for humans, is it reasonable? Well, or deer, it might be, it's reasonable in the beginning, but remember, for most populations, as the populations grow over time, they can't keep growing at the rate dp dt equals k times p. Because that would represent exponential growth, and populations normally can't keep growing exponentially forever because they run out of resources like food and space and so forth. But for like bacteria, in a petri dish, bacteria, bacteria in restaurants bacteria can spread very quickly. And that's why, we have to have good food handling practices, right, in restaurants, because bacteria can spread quickly. How many of you maybe have worked at a restaurant and have noticed that? Has anybody done that yet? I did when I was your age. Any of you? Okay, John knows what I'm talking about. Did anybody wash dishes like Dr. Duty here? Or serve some tables? I assume some of you did. All right. Good experience. Okay, so I want to just move down here. So this dy dt equals ky, all right, they sometimes call it the law of, well, they're calling it the law of natural growth. I call it the law of exponential growth. But why would I do that? Well, look, dy dt equals k times y is a separable differential equation. And if you separate the variables here, which isn't hard to do, you'll get a solution. So if your differential equation is dy dt equals k times y, okay, and then y is equal to a times e to the ktth power. Okay, and so when you have this type of differential equation, you get the solution is an exponential function. Okay, and so that's why we call it exponential growth. Are there any questions on that general idea? Are there any questions? All right. So I'm just looking here. All right, I want to go ahead and look at a problem here from a problem I'm going to give you. So the book talks about different applications of, this exponential growth model. And one of the applications, let me just, like the population growth is an application. I mentioned that. You could have radioactive decay. Okay, how many remember radioactive decay, dealing with those kind of problems in pre-calculus? How many recall that? Absolutely, and thank you, Tyreek, thank you, Josiah. And in pre-calculus, you were given the solution for exponential decay, an exponential solution. But now you know how to derive that because you can separate variables for the differential equation for exponential decay. So that's a good thing. Let me just see here. There's an example on Newton's law of cooling. In your homework, you're going to have some Newton's law of cooling problems. I believe that's example 4. Yeah, and Newton's law of cooling is dt, where T is the temperature of the object at time t, and Ts is your ambient temperature. The rate of the dt is proportional to the difference between the temperature of the object at time t and the ambient temperature of the surroundings. But the thing is, if you do a substitution where you let t minus t sub s, and that's going to be some constant, the t sub s, if you let that equal y, then since y prime of t is t prime of t, you'll get dy dt equals k times y. Okay, so Newton's law of cooling, they have a nice example, and you can look through that. And what I'd like to do is do an example with you here of my own that deals with bacteria growth. But we are a little limited on time, so what I'm going to do is let me stop the sharing of the application here, and let me go right to the example I want to share with you. Okay. And I have it written out here. Okay. And I think in the interest of time, this is going to be exercise 2. Okay. This is exercise 2. From your book here. Actually, go ahead and copy it down. I mean, I think it'd take like 5 minutes to copy that, so we'll have time to cover it. Go ahead and copy it in your notes. That's fine. Okay, so people are copying this example down. That's fine. Okay. All right. So in this problem, a common inhabitant of human intestines is the bacterium E. coli. A cell of this bacterium in a nutrient broth medium, okay, like, you know, chicken soup, something like that, or, well, I'm not an expert on broth, but maybe vegetable broth, you know. A cell of this bacterium in a nutrient broth medium divides into 2 cells every 20 minutes. The initial population of the culture is 60 cells. We want to find an expression for the number of cells after T hours and then find the rate of growth after 10 hours. Okay. So if a cell of this bacterium divides into 2 cells every 20 minutes, okay, if that's the case, can we say that the rate of growth is proportional to the size of the population? Would that be based on the information given here? Can we say that the rate of growth is proportional to the size of the population? In other words, that we can. And I want to be, you know, that's right, John. We can say that. We can say that. This is definitely represents exponential growth. If you have a cell that's dividing into 2 cells, and then each of those cells divides into 2 cells, and the process continues, that's exponential growth. Now, what we want to do is, if we want to find an expression for the number of cells after T hours. Now that number, that could be, you know, we could call that population P of T. We could call the population Y of T. Okay, and we're going to call it Y of T. So let's go to the next page here and look at the solution. Okay, so this is our solution. Hold on. So what we're going to do is we're going to let Y be the population of E. coli, example solution. We're going to let Y be the population of E. coli after T hours. The rate of growth, dy dt, that's your rate of growth, is proportional to the size of the population. Okay, and that means since that's the case, we can say that dy dt equals k times y, because this says the rate of growth is proportional to the population y at whatever time. So is proportional to means equals k times y. Now that is, and we're also given the initial condition that we start out with 60 cells, right? We start out with 60 cells initially. Now in the book, you're told that a solution, well, you're told there the second formula in the section 7.4 lays out the solution for this differential equation with this initial value. The solution is going to be y of t equals 60 times e to the kt. The e to the kt, you know there's going to be an exponential term in there, but we have to figure out k. That's called our relative growth rate. And the number in front of the exponential function is always the amount that you initially start with. What I've done over here is I've shown you, I've formally derived this result for you. dy dt equals k times y. I separate the variables here, okay, and I formally go through the steps so that you can see how we got that solution. Okay, are there any questions on that? All right, well, to answer the question, find an expression for the number of cells after t hours, that's y of t. We're not quite there yet because we have to figure out what k is, right? I mean, we have to figure out what our relative growth rate k is there. So, well, how are we going to do that? Is there a piece of we need a piece of information to help us solve for k. Okay, what are we told? What else are we told in the problem? I see that the bacterium divides into 2 cells every 20 minutes. Okay, so we can make use of that. We can make use of that. So after 20 minutes, how many cells should there be? We're starting out with 60 cells. So after 20 minutes, how many cells should we have in here? Well, if the cells were to be split, we'd have 30, but it's being doubled, so it would be 120. That's right. Thank you, everybody, for your participation. Thank you. So, yeah, 60 cells. Each cell divides into 2 cells every 20 minutes. So after 20 minutes, 60 cells becomes 120 cells. So what I'm going to do is I'm going to replace the y of t with 120. And what t would I put in there? What t would I put in? Am I going to put in 20 for t for 20 minutes? Or am I going to use a different value for t? If we look at the original problem, we want to find an expression for the number of cells after t hours. Hours, right? So am I going to put, whoops, am I going to put a 20 in for t if I want the expression to be in terms of hours? We're not going to put in 20 minutes. We're going to put in, right, 1/3 of an hour. That's right, John. So we'll do that. We'll put 1/3 in. So 120 equals 60 times e to the k times 1/3. And now we can solve. And you've done these kind of things before in pre-calculus, but what's nice here is, like in pre-calculus, you would just use the formula, find k, but you wouldn't know why the formula was true. But now you know, because the growth rate is proportional to the population, using separation of variables, you can solve the differential equation to get this answer, which is very nice. All right, so, but now let's get back to the matter at hand. We have to solve for k. So we don't want the exponential, the e there. We want to get negative 1/3 k, or 1/3 k, I should say. We want to get 1/3 k down. So we got to take the log of both sides. If we do that, then k will equal 3 times the log of 2. And so k equals the log of 8. If you have 3 times the log of 2, that's the log of 2 to the 3rd power, which is the log of 8. Are there any questions on that? Okay, well, so now y of t is going to equal 60 times e to the k t. K is the log of 8. And e to the log of 8 can be expressed as 8. So you see I have e to the log of 8 times t power, but I can rewrite that as e to the log of 8 raised to the tth power, and e to the log of 8 will equal 8. Okay, so remember, WebAssign wants exact answers. So if you were to do a log of 8, approximate that, and write 60 times some decimal to the tth power, WebAssign's not going to accept that answer. It wants the nice, beautiful answer. Okay, and why wouldn't you want this answer, right? So now we have an expression. Now we have our expression, you know, y of t equals 60 times 8 to the tth, 8 raised to the tth power. But now we want to find the rate of growth after 10 hours. Okay, so rate of growth, when you hear rate, what do you think? What word comes to your mind as calculus students when you hear the word rate? Derivative, exactly. So I know what y of t is. I know what it is. I'm going to take the derivative of y of t. So if we do that, the rate of growth is dy of t. And so if I go back here, and I'm sorry about that, I can't stop that, but I think you can hear me fine. So you're using the derivative d dt of a to the tth power. Okay, and you have a formula for that. The derivative of a to the tth power is the log of a times a to the tth power, right? And I do want to finish here because I know it's 2:05. I just need a minute. So there's my derivative. And so after t hours, the growth rate, after 10 hours, the growth rate would be dy dt, but t equals 10, not 2. That should be a 10 there. Okay, so hold on. Thank you for being patient. So when t equals 10, the growth rate is 60 times the log of 8 times 8 to the 10th power. And then that's going to be equal to 1.3397 times 10 to the 11th cells per hour. And then if you write that out, in WebAssign, they're going to want the answer in terms of billion cells per hour. It's a rate, right? So dy dt, y is the number of cells and t is in hours. So, but they're not going to want this answer. They're going to want you to write your answer as some, I think it's a decimal accurate to the second decimal place in billion cells per hour. Okay, so this is what they're going to want, something like this. But I think it's a great problem. And are there any questions before we stop today? Any questions at all? Okay. How many think this is a cool, kind of a cool problem? You can see how fast this bacteria grows. Yes. Yes. Thank you, John. Any other? Thank you, Josiah. Thank you. Thank you, Francesca. And you're starting to really learn things. You know, you're really learning things. All right. Well, very good. Very good. Well, I will stop here if there are no questions, and I'm going to head over to my office hours, the office hours session. So feel free to join me there if you have any questions. Thank you, Dr. Carbone, for sitting in here a little bit on our class too, on the class. All right, thank you, and I'll stop there.